Hey guys, in this video we're going to talk about electrolytic cells. So you've already learned the first half of this unit of electrochemistry, which is the galvanic cells. Now electrolytic cells are a little bit different, so make sure you're able to distinguish the two. First of all, you have to be able to recognize if it's a galvanic or electrolytic cell. Remember that galvanic cells do not require an outside power source. It creates a power source on its own. It creates a battery. So the reaction happens on its own. It is thermodynamically favorable. Electrolytic cells, on the other hand, are reactions that do not typically happen on their own. And so what we have to do is hook up an outside power source like a battery or some sort of external power connection in order to create this reaction to actually happen. So we have electrolytic cells that are thermodynamically unfavorable. Now, one thing that's really important is the sign conventions for electrolytic cells. So we have E cell, which is our standard E cell values. We've learned that in galvanic cells, we have positive E cell values, but in electrolytic cells, we will be getting negative E cell values. Also, when we look at delta G, delta Gs are going to be positive. And remember, that indicates that the reaction is thermodynamically unfavorable, meaning that the reaction does not happen on its own. You have to have something to force it to occur. So let's talk about our anode cathode. How do you figure out who's reduced? How do you figure out who's oxidized and things like that? So that's what this video will cover. And so just like in our galvanic cells, your anode is always going to be where the species is oxidized. Your cathode is always going to be where the species is reduced. So that hasn't changed. Oxidized at the anode, reduced at the cathode. Also, what hasn't changed is that our electrons will also still travel anode to cathode. That hasn't changed either. So these are the same things whether or not you're dealing with a galvanic or an electrolytic cell. What's a little bit different about electrolytic cells is how you determine who is going to be oxidized and reduced. Now remember that when we were working with galvanic cells, we had to look for that chart that had standard reduction potentials on it. And so we looked it up and we saw that the positive value, more positive value, was the species that was always reduced. For electrolytic cells, that's a little bit different, okay? You do not look at those standard potentials and you do not decide who's oxidized or reduced based upon which is the more positive value. Instead, you have to look at the species that is in the solution. So let's look and see how this is a little bit different from galvanic cells. Remember when we had galvanic cells, we had two different half cells. So we had two different containers with two different solutions. In electrolytic cells, however, you will have just one single container and both of your electrodes go into that single container. Now, because of that, we only have one solution only that is in our cell. And so in order to determine who is oxidized and who is reduced, therefore who's the anode and who's the cathode, we are going to look at that solution. All right, so there are a couple of rules that we have to pertain to whenever we are looking at our solution. If the solution is not aqueous, so let me explain what that means. Remember, aqueous solutions are where you take your ions and you put them in water. So water is involved in aqueous solutions. You can, however, have instances where water is not in here, okay? And that would be in the molten state. Now, what that means is that you have just taken that solid and liquefied it. So if your solution is not aqueous, meaning it doesn't contain water, it is just a pure molten or liquid state of that solution, then the rule is your cation of that solution is always going to be the species reduced. And the anion of that solution is always going to be the species oxidized. So let's go through an example problem with that. So what I have here, I'll use red, is a solution of tin chloride. So tin 2-chloride is SnCl2. Now, how I know if it is an aqueous or molten state is the molten state will have a little liquid right there. That's a little cursive L. The aqueous state, we've seen this many times, has the little AQ right there. So this tells me, this little liquid symbol tells me that I am just going to follow these rules. The cation is going to be reduced and the anion is going to be oxidized. So what is our cation? What is our anion? Our cation, remember, is the positively charged thing in the compound. Our anion is the negatively charged thing. So Sn is our positively charged thing, because if we look at the charges or we look at the oxidation states, Sn is a 2+ oxidation state and Cl is a -1 oxidation state. So here's what's going to happen. He's my cation, so he's going to be reduced. He is my anion, so he is going to be oxidized. So let's write our half reaction for our cation that is going to be reduced first. So we take 10, we apply it as its charge. There will be 2 electrons transferred, and that makes 10 solid. So this is the reduced half reaction that we have there. Now let's write the half reaction for the oxidized species. So we said Cl2 is going to be the oxidized species. So we're going to start with Cl2, which is minus charge. Oh, that's my bad. It's not diatomic if it's charged, right? This is a mistake that a lot of you guys make. I made the same mistake. So this is my ion. It is charged, okay? So it will go to Cl2. Now, when you write the half reactions for these halogens that are diatomic, you have to first make sure that you balance your elements first before you put your electrons on there. So do you see how I have Cl2? I'm going to have to put 2 Cl minuses on this side. Now, how many electrons does that mean is being transferred here? We have 2 minus going to 0. You see how that's going up in charge, right? So there's going to be 2 electrons that chlorine is oxidized by. And so this is my oxidized half reaction. Now, how do I kind of fit this in and label my electrolytic cell? Well, one of these electrodes is going to contain tin, which is a solid. And so we are going to have Sn just labeled as one of those electrodes. Now, which electrode will that be? Will that be the cathode or will that be the anode? Well, since this is the species that is reduced, this is going to be my cathode because reduction occurs at the cathode. Now, let's talk about what is going to be at the anode. So our anode is going to contain Cl2. Now we've run into a little bit of a problem here. Cl2, if we know kind of what how it naturally appears at room temperature, Cl2 is a gas. It is not a solid. So this electrode here has to be a solid. It has to be a metal in order to help my electrons be transferred to and from and whatnot. And so if Cl2 is a gas, what do I use for this electrode? I use what we call, and I'm going to put this up here, an inert electrode. So there's a definition type thing that you need to know here. What does the word inert mean? Well, inert means that it does not react. It's non-reactive. So the only purpose of this electrode here is to have these electrons be transferred through and not react with anything. And so there are 2 things that we can add in here as an inert electrode. And that is platinum. So platinum, the metal, and it's abbreviated as PT, or carbon in the graphite form. And we all know what carbon in the graphite form is. That's our pencil lead. So we've experienced this on the daily, right? And so you can use platinum or graphite as an inert electrode. And what that is doing, and the reason why I have to use it, is it's allowing my electrons to move through this piece of metal here, but it's not reacting with anything. Now, why is it necessary? It's only necessary if your species that is supposed to be present at that electrode is a gas, and it's not a solid, okay? And so we have chlorine here, which is supposed to be our electrode, but because it's a gas at room temperature, we are going to put either platinum or graphite in the place of that. Now, what will we witness here? Well, because chlorine is a gas, remember when gases are produced in solution, we'll actually see little bubbles kind of being made in that solution. And so those bubbles will be the chlorine gas that it's produced. Now, we've taken care of both of these things here. We've said that's our anode and that's our cathode. What is our solution labeled as? Well, that's the solution that we started with. So the SN2+ ions and the 2Cl- ions are here in that solution. And remember, it's a molten solution, so it's in liquid form. So do you see how we find our anode and cathode are reduced in our oxidized species just a little bit differently than we did for galvanic cells, but the same idea still approaches. Now, let's talk about our electrons. How do our electrons travel here? They still, like before, travel from anode to cathode, so that hasn't changed. All right? So this is how we figure out our species that's reduced, our species that's oxidized, and we can be able to answer our half reactions and our cathode anode information from there. All right? Now, this is if we have a molten or liquid state. What if we have a solution that is aqueous? Well, there's some rules that we have to abide by here. If the solution is aqueous, we have to double check our cation and anion, okay? And so if we double check our cation and anion, these rules apply. If the cation is a group 1 or group 2. So remember, that's group 1 or group 2 on your periodic table. That's the first two columns on the left-hand side. If your cation is a group 1 or group 2, those cations will not be reduced. Water will be reduced instead. Now, when water is reduced, it creates this half reaction. 2H2O plus 2 electrons yields H2 plus 2 OH minus. So what we're actually going to see present there is H2 gas. Now, because this is a gas present, again, we're going to have to use the inert electrode if that is what occurs there. If your anion is a polyatomic ion, okay, so we're looking at our anion now, we have to double check it. If the anion is a polyatomic ion, that polyatomic ion will not oxidize. Instead, water will be oxidized. Now, when water is oxidized, it forms this half reaction. 2H2O yields O2 plus 4 H pluses plus 4 electrons. What we will see produced there is oxygen gas. So like before, if we have oxygen gas that appears to be produced at the oxidized, so anode, we will again have to use an inert electrode there because it is a gas. So I'm going to go through an example problem with the solution if it is aqueous. So let me take a second to